This is the worked out solution for AP Physics C Mechanics 2010 problem number 1. This is the coffee filters experiment. So let's see. We have some number of coffee filters being dropped, and the students change the number of filters, and that of course changes the mass, and same shape, so on and so on. So in part A, the students suspect that the drag force F sub D is proportional to some constant c times the velocity squared, where c is a constant. Using this relationship, derive an expression relating the terminal speed v of t to the mass m. Well, we've seen that before. At terminal speed, net force is equal to 0, right? Because it's reached a constant speed. So no acceleration means no net force. That means that the drag force must be equal to the gravitational force. So CV squared must be equal to mg. So V would be equal to mg over c square rooted. So that is an expression for the terminal velocity. And in part B, we are given a data table of what the students got experimentally by dropping, it looks like 1, 2, 3, 4, and 5 filters, if you look at the masses. Not that that really matters, but probably that's what's going on. And part 1 of B says, assuming the functional relationship for the drag force above, so assuming this relationship, use the grid to plot a linear graph as a function of m to verify the relationship. Well, let's see. The data that they have, they've got terminal speeds and masses, and so do we. That's a constant and that's a constant, right? That's the constant we're looking for. So if we wanted to graph, let me rewrite that a little bit. So my two variables are VT, these are the things that they collected in their data table, and the square root of g over c, which is just some constant, times the square root of m. I just split this up, right? So if you think of this as y equals mx, that's what we want. We want to get a straight line. So I could graph this as y and the square root of m as x. That's what I could make the, this would be my x-axis would be the square root of m, and the y-axis would be the terminal velocity. And then my slope of that line, when I find that, I think in the next part, will be equal to this. That's one way to do it. Or you could square both sides of this equation and say terminal velocity squared is equal to g over c times m, and then graph that on your y-axis, terminal velocity squared, graph mass on the x-axis, and then the slope will be g over c. It's up to you which way you want to go, but you know, given a choice, maybe we don't want to have more square roots than we need. So I think I will choose this. So you notice in the data table that they give you the option, like they use the empty boxes in the data table as appropriate to record any calculated values you are graphing. So we're going to go ahead and graph v squared here. We're going to fill in this line and square all the velocities, and then graph this on our x-axis and this on the y-axis. If you went the other way, then they expect that you might put the square roots of the masses up here, right? So they gave you room to go either way, but you only need to do one or the other. Okay, so filling in the bottom of the table, VT squared, and the units we should put just like they did, right, in their table. Notice that they have kilograms here, meters per second here, so I'm going to go ahead and that would be meters squared, seconds squared, right, because it's the velocity squared. And then squaring those numbers, let's see, that would give us 0.51 squared is 0.26. 0.62 squared is 0.38. I'm sticking with their two significant figures. 0.82 squared is 0.67. 0.92 squared is 0.85. And 1.06 squared is 1.12. So those are my v squared values, and I would fill those in right here and label my box as terminal velocity squared. And then you go ahead and graph them. Now let's see, if you look at the graph that they gave, we have 1, 2, 3, 4, 5, 6 spaces here, and this goes up to 5.1. So I would label this on the bottom, I would label that as mass. Oh, actually, you know what they said here? As a function of m, not as a function of the square root of m. So I think maybe we have to do it the way that we chose here. They didn't say, maybe they didn't give us the option of the square root because they put this in here for us. So I think we chose the right way. So let's see, how are we going to label this? Well, this could be, I could label it as this is mass in kilograms. So this here could be 1 times 10 to the negative 3, 2 times 10 to the negative 3, and so on, right? And then you can work out your decimals. This would be 1.2, 1.4, 1.6, 1.8. So lucky for us, we have base 10 to work with. And here we would have v squared, terminal velocity squared, which is meters squared seconds squared. We should label the units there. And this is 1, 2, 3, 4, 5, 6 also. And we need to go from 0.26 to 1.12. So I think that's going from like 0 to 1.2. So that divided by 6 gives me 0.2, 0.4, 0.6, 0.8. 1.0 and 1.2. We're a little bit spoiled having the calculator and the computer do these things for us, so a little bit of practice scaling like this is probably a good idea. Now, let's go ahead and graph. I'm going to need for, let's see, I'm going to go into, what's going on here? I'm going to go into the lists, edit, and clear. Don't go into L1 and hit delete. Remember, that causes all sorts of problems. Just go to L2 and hit clear. Okay, so my x-axis, I want to have the masses of these things. So that is 1.12 times 10 to the negative 3. Enter. And see, the calculator converted that to a decimal for me, but I'm just going to keep entering them like that. Oops. So to the negative 3. And 2.96 times 10 to the negative 3. And 4.18 times 10 to the negative 3. And 5.1 times 10 to the negative 3. And just check, make sure those look good. Looks like I entered them all correctly. And then here we have our terminal velocity squared, right? And that's what we want on the y-axis. So 0.26, 0.3. By the way, you don't have to do this with your calculator. They are okay with you graphing the points and sketching a line of best fit, rather than using your calculator to actually find the regression line. I'm more comfortable doing this. You're still going to have to plot them by hand with a calculator, and I've left that part for you to do. I think what we're really doing now is the second part of B, which is use your graph to calculate c. So if we have graphed this, then my slope is equal to g over c, right? Because there y equals mx. So that's how we do that. So I'm going to go ahead and go to quit out of there, stat, calculate. I want linear regression, number 4. That'll automatically do L1 and L2. That's the default. And it gives me a slope. It's ax plus b, so a is the slope, of 216. So let's see. 9.8 over c is equal to 216. So solving for c, that would give me 9.8 divided by 216. So c looks like is equal to 0.045 or thereabouts. Okay, the next part, C. I hope we used a lot of our 15 minutes there. Let's see how long this takes us. Sketch an approximate graph of speed versus time from the time the filters are released up to the time t equals t that the filters have fallen the distance y. So in other words, it's very close to terminal speed by the time they fall in that distance. So all that means is we better get real close to the terminal velocity. Indicate time t equals t and terminal speed v equals vt on the graph. All right, that's pretty easy. We did something real similar to that last problem. So we have velocity, and really this is speed, right? They're only giving us a positive option here. So let's call this the terminal speed. We know it's going to be asymptotic to that. And we're dropping them, so it starts from rest. They wanted to indicate time t on the graph where it's reached, where it's very close to terminal velocity. And I think that's it. So we know that we start with, as you drop them, they would initially have an acceleration and slope of 9.8, and then very quickly, as the drag force kicks in, we get a graph that looks like that. What they'd be looking for is that the graph is concave down, that it's very close to Vt by the time you got to time t, something like that. That's part 1 of that, and then in part 2, suppose you had a graph like this one that had a numerical scale on each axis. Describe how you could use this graph to approximate the distance y. Well, that's a calculus question. If they're asking how could you use a graph to approximate something, there are two possibilities. Either they're talking about slope or area. In other words, a derivative or an integral. And if you think about the units, that will always point you in the right direction. So this is time in seconds. This is velocity in meters per second. And they want us to approximate y. So what is y equal to? The distance that the object fell is equal to, let's see, if we did meters per second times seconds, in other words, if we find the area under that curve, that is how you do it. So we take the integral from 0 to t of the velocity graph, and that would give us an approximation for y. So I'm just going to write a little bit more because that might be enough, but I say approximate by finding area. That should satisfy them. D, determine an expression for the approximate amount of mechanical energy dissipated, delta E, due to air resistance during the time the stack falls some distance y, where y is greater than y. In other words, so like by the time you've reached terminal velocity. And express your answer in terms of y, m, v, t, and fundamental constants, which usually means g, or it could be capital G if you're talking about orbits and such things. So let's see. Initially, if we've dropped the distance lowercase y, initially our energy would be all potential before we dropped it. That's mgy. And finally, at the end, after it's dropped that far, it only has kinetic energy, right? Because it's dropped that, and this is our 0 point, right? We're using that as our reference point, y down to 0. So its final kinetic energy would be 1/2 mvt squared, right? And so initial energy, this is our final energy. It's going to lose some energy, so we would expect that the change in energy is this is equal to delta E. If no energy was lost, then this minus this would be equal to 0. That's what I almost started to write there. But that would be no, right? That would be when those two are equal to each other. But we lost energy to the frictional force. So this minus this is our change in energy. Now that's not one of the constants. Oh, that is one of the constants that they wanted us to use. So I guess we're done. That's it. I thought maybe they wanted us to go back and plug this in, which I think they wanted to do in some wanted us to do in some other problem that we looked at. We could have done that, and if they said use C instead of the terminal velocity, but this is all they wanted us to do here. So we're done. And we made it in there at 17 minutes, and there was a lot of talking, so we'll see. And we'll see if YouTube lets me upload that. I think I might be capped at 15 minutes.